So this is, so I want to share a couple of things with you. What I want to show you here is that if you go, I guess, right here, let me go to Physics 11. And if you come all the way down to the practice exam, what I started doing here is that here's the question for the practice exam. And if you click on this, this is actually the video solution of this problem. And this is supposed to somewhat replace me, because the last time we did the practice exam, we did it live, and I would prefer to do it live, but it would actually take too long, and I can't, my knee can't handle that much time. So here's a solution that's up on YouTube, and then here's the following notes for that. And you could see that I've done 2. I'm done with 3. I haven't recorded it. I'm done with 4. I haven't recorded it, and I haven't done 5 at all. But you know, that's just going to take me about 2 hours to do 3 and 4, and then 5 sometime later on. Hopefully this evening it gets loaded up so that you have this. So those are the things I wanted to show you. And if I have an opportunity, I will do a second practice exam the exact same way, just to try to prepare you to the best of the ability that I can. Now, technically, this is the last day that I will cover any new material. And the nice thing about it is that I think the material from here gets easier if we can follow some of the steps. So what I'd like to do is that I'd like to go through the practice exam and then bring in conservation of energy so you could get a sense of what works best for you. Because you could either do the work energy theorem the whole time, or you can do conservation of energy. So it really is up to you what works best for you. Conservation of energy is typically the way to go, though. So this is what we did last time. These were our examples that we were going through, and that's what we want to focus on. And what we see here is that we started to do example 7.2, and we only did A. And we had a car that had 1110 kilograms, and it accelerates from 10 meters to 28.6 meters. And we wanted to find the work done by the car. And so what we ended up doing here is that we isolated the car, and because we isolated the car, then the only way the car could accelerate if there was an external force. And what we said the external force was, it had to be the work of friction, or the work of the road. So it's the work of the road that changes the speed from V1 to V2. And so a bar diagram shows us that the kinetic energy at 1 plus the external work of friction, that changes it to its final kinetic energy. Once again, K1 and K2 don't mean very much, only the external work means, which is transferred. So then, using the work energy theorem, we set up that the work of friction does cause this change in kinetic energy, and we ended up calculating that the work of friction was then 398,000 joules. So now I want to get to the second question. And the second question here has to do with the work done by gravity. It says that the lowest point in Death Valley is 85 meters, or negative, it should be negative 85 meters. That's a typo. Or that's negative 282 feet. So again, that's a mistake. This should have a minus sign right there, because it's below, or you could say it's 85 meters below sea level. I guess I don't have to put a sign if I clarify that below sea level. The summit of nearby Mount Whitney has an elevation. Again, this is not correct. The reason why that's not correct is that the height of Whitney is actually around 14,000 feet. I believe it's the only 14,000 foot climb in California. So it's actually Whitney Portal, if you know what I'm talking about. So when you climb up to 4,420 meters in elevation change, what is the change in gravitational potential energy of an energetic 65-kilogram hiker who makes it from the floor of Death Valley to the top of Mount Whitney? Again, it's not to the top of Mount Whitney. This is the portal. Okay, so I should clarify that and write that this is, so when I say this, I really mean what's called Whitney portal. And it is actually quite hard to get permits to go up from Whitney Portal to the top of Mount Whitney. So this, believe it or not, is about a race. So this is actually a running race. It's an ultra marathon, and it's called the Bad Water Marathon. It's an ultra marathon. So it's the Bad Water Race. And the Bad Water Race is 135 miles. And the crazy thing is that when you look at the profile of the race, it looks something like this. And there's some crazy thing that goes on here. So this guy right here is actually, Badwater is in Death Valley. And you can see here is that this is Whitney Portal. So Death Valley, man, it can, there's some races where it's actually 120 degrees. You're running in 120 degrees, which is insane. And people do some really imaginative things here. So they start here, and as they're going through here, and this is where it ends. I mean, I've seen people do coffins of ice. I mean, they change shoes. They, a zillion times. They have a whole team that follows them. It's a very different mentality. So if you look at the details of the race, okay, so here's the details. It turns out that you have a horizontal distance of 135 miles. So in this case, as you are running, right? As you are running, what you're actually doing here, what makes you run, as you already know here, is that you have a normal force. So when you look at this thing, you have a normal force that comes out at an angle. Maybe we should say that's the force of the ground. Maybe we should do that. That's the force of the ground. So then we have to pay attention to two forces. One is the normal force, but we know that that normal force is really counteracting gravity. And the other force is, as you push off, you are doing what? You have to deal with the force of friction. And in this case, we hope that you're only doing static friction. So what you're finding here is that the work against friction, that's going to change your energy. Now there's a second piece to this. It turns out that there's a vertical distance of 2.8 miles. So when we talk about a vertical distance, there's only one vertical force. So when we're talking about this vertical distance, we have to have a picture that looks vertical like this. And now we have our runner, right? We have our runner, and our runner, wow, this is harder to draw at an angle. Our runner is running vertically. So in this case, we think about the displacement being in that direction, but now the only force that we have to counteract here is gravity, and now we have a displacement that's in the y direction. So it's the work of gravity that we really want to imagine, because the question then reads like as we said here, what is the change in gravitational potential? Gravitational potential is the stored work of gravity, which we then call potential energy. So in this picture here, we're going from minus 85 meters, and then I think they said that the height change was 4220, and then we're going to go to a height of plus 4220 meters. That's what we're paying attention to. So we now know what we're actually doing here. This guy is going to be the negative work of gravity is going to change the energy. And the way we call this energy here is the gravitational potential energy. So let's write that. So from the work energy theorem, here's what we have. We have the negative work of gravity must be the change in gravitational potential. And in this case here, what happens? We see here that as we go, right, we're climbing this. So we could then say that this is a positive work done by our legs or friction. Okay, this is going to be the positive work of friction as we go up. So this is a positive quantity. So our body does positive work, and as a consequence, it increases potential energy. So when I look at my picture, what I'm really seeing here is that I'm seeing a picture that looks something like this. I have a certain amount of gravitational potential. And in this case, it's actually negative. So this is the potential of 1. Now the question is, why is this negative? Because if this is sea level, and the way they're giving us the numbers, we're saying that that height is 0 here. And we said that associated with this guy is minus 85 meters. Now, we store the work that we do into the gravitational field. So now if I go and I do work here, right? I do work. I then do gravitational work. That gravitational work is a positive quantity, or I could say it's the work of my legs as I go up. And as a consequence, when I combine these two, I have now increased my gravitational potential energy to this point. And once again, No, I probably should have done this a little bit higher. I think I'm going to change it just to make it a little bit cleaner. Okay, I want to do this a little bit cleaner. So if I go up just one more square, and I go up one more square here, then we can actually make it a little bit cleaner. Because now we can see here that the change, so if this is 1 and this is 1, 2, 3, 4, then you could see here is that this whole quantity right here is the change in gravitational potential energy. And as we said before, this is the only meaningful thing we could talk about with the energy here. So now I can compute that. I know how to do that. So if I look at the change in potential energy, so then the change in gravitational potential energy is in the negative work of gravity. But the negative work of gravity is then going to be the change in gravitational potential energy, and that guy is going to be mg times the height change. And if I look at this, then this will then be a height change goes something like this. We know the mass of the runner is 65 kilograms. And we know that the height change is going to be 4420 minus 85 meters. And that quantity gives us 4505 meters. So then if I plug in my values, I'm going to get 65 kilograms times G times my height change. And when I compute that number, that turns out to be 2.87 times 10 to the 6 joules. Now, I guess the question that we want to ask, so in the metric system, this is what we calculate. And the question we have to ask, what does this number mean? Because we're not used to the units of joules. What does this mean? Well, let's convert to calories, because that seems to make more sense to us. So if I look at the potential energy change, this is going to be 2.87 times 10 to the 6 joules. But then our conversion, it's roughly 4,200 joules for 1 calorie. Let's call it a cal for right now. And if you add that up, that's 683 calories, right? And you got to admit that this is surprisingly a very low value, right? If you have a shake, you would, it's not even close to a shake, right? Shakes can be as much as almost twice as much as this. And the way we really look at this is that you have to remember there is a horizontal distance of 135 miles, while the vertical distance is what was it? I think I said it was 2.8. Yeah, 2.8. This is extremely small. Height change over 135 miles. So most of the calories are actually used up running horizontal. So most calories are used to go horizontal. My guess here is that, man, you got to be consuming some serious calories. I would guess somewhere between, I don't know. I mean, you'd probably consume just to make it, right? You would probably consume, is consume 2 M's? I think it is. You would consume, I don't know, somewhere between 15 to 20,000 calories. You would have to be feeding yourself quite a bit in order to make that through. Okay, let's go to the next one here. And this is C. So C involves a spring. So let's focus on this spring right here. And it's asking the question, how far must you stretch a spring with a K constant of 1,000 newtons per meter to store 200 joules of kinetic energy here? So we need to set up a picture to make sure that we're actually getting the right picture. So what I would imagine here is that suppose we start with an unstretched spring. So what do I mean by that? Well, I imagine that I have my surface here, and now I have my spring attached, and I imagine that this is my block right here. So if this is my block, I'm going to focus on just the center of this block, and I'm going to say that this distance represents the point where the spring force is actually equal to 0. And because of this, I'm going to call this x equal to 0, which is our equilibrium point. So now what I'm going to do is that I'm going to stretch the spring out. So if I stretch this spring out, let's say that I stretch it to some point over here. And so when I go to look at this thing, I'm now taking the rungs and really spreading them out. And so the only thing that I know here is that I have moved this guy some distance, delta x, from here to there. So if I call this, let's call this x1 equal to 0, I'm going to call this x2 exactly the distance that we need in order to get there. So what happens here? I look at this system and I see it has, if I have 0 energy in my spring here, then I'm going to say that initially there is 0 energy in the system. So now what I'm going to do, my work of my hand is then going to do positive work. So in other words, I'm going to come in here and I'm going to do positive work right here. So this is the force of my hand. As I pull this guy out, in that direction. And I know here that my displacement is in that direction. So that work does positive work. But then all that work that, oh, you know what? I said force of my hand. I should have been more careful, and I should have said the work of my hand. So now that work of my hand does not disappear. It reappears as stored work. And so this is the spring potential at 2, and this was the spring potential at 1. So when we calculate the work, the way we did this here is that we have to talk about the area. And as we have to talk about the area, we said here is that if I had a spring that looks like this, and this is my spring, and this is my distance, what I'm going to do here is that I'm going to do work. How's my work going to go? I'm going to start off at x1 equal to 0, and then I'm going to pull it because the spring force we said was minus kx. So when I look at this, I went all the way to x2. So then if I want to calculate the work done or that got stored in the spring, I have to calculate the area of this triangle. Right? I need this area of this triangle, and you could see that it's half a rectangle. So then, here we go. According to the work energy theorem, right? The work energy theorem then says that the work of my hand is also the negative work of the spring. That work gets stored in the rungs of the spring, and this is equal to the change in the spring potential. So then, from what we showed last time, this would then be 1/2 kx2 squared minus 1/2 kx1 squared. And remember, that's the area of the triangles. Okay? Remember, these are the areas, right? We're calculating areas. So then, because x here, 1 is 0, this whole term goes to 0. So when I look at the spring potential energy, it's 1/2 kx2 squared minus 0, but we're given a couple quantities. One, they tell us that the spring potential energy stored was 200 joules. They tell us that K, the spring constant, was 1,000 newtons per meter. So what we're solving for is what is x2? So let's go solve for this. So now I need to isolate x2 from this equation. And so if I look at that, you could see here is that there's a square root. So when I look at this, the square root of 2, I have to have a square root. So on the left side, you could see that I have the change in the spring potential energy, and I have that 1/2. So if I multiply both sides by 2, I'm going to get 2 delta US. And then I have to divide everything by K. And there's my relationship right there. So now if I just plug in my numbers, I'm going to get 2 times 200 joules. And then my spring constant is going to be 1,000 Newton meters. And then I got to take the square root of this. And when I compute that distance, I get 0.63 meters. And that's the distance of x2. Now, note that x2 is meaningless. Why would I say that x2 is meaningless? If I just give you that this is a point x2, that means nothing. What it means here is that we have to have a reference. And where's our reference? That is our reference. We are pulling it from 0. It's not always 0, though. Conservation of mechanical energy. So when you see the practice examples for practice exam 2, you're going to see that problems 3 and 4 are going to be particularly long. Why? 1, I do it with the work energy theorem, and then I come back and do it with conservation of mechanical energy. So we need to think about a picture here. So according to the work energy theorem, it says here, if there is work done by an external force, that work can change the energy of the system. So what do I mean by that? That means this could be the change in kinetic energy, the change in gravitational potential energy, and also the change in the spring potential energy. This is one way of looking at this thing. So what that means here is that if I isolate an object, and this is what we mean by isolating an object. I have an object, and for the sake of argument, let's say that this object is a block. So that is my object. So I isolate it. Now, the one thing you gotta pay attention to is that, look what this tells me about. This guy tells me about the force of gravity. This guy right here tells me about the spring force. So if in my system, if the system includes gravity and the spring force, so in other words, if I have this system and I have a spring in this system, gravity here, or I have a spring system like this, in total energy, these guys are not considered external forces. So we need more mathematics to actually explain the details of this. But if the system includes gravity and the spring force, these forces do not change the total mechanical energy. So picture-wise, I'm going to make it more simple here. So if W external is equal to 0, then the total energy of the system which we call mechanical energy, we could see here that then the mechanical energy before must equal the mechanical energy after, where the total mechanical energy is equal to the kinetic energy plus the gravitational potential energy plus the spring potential energy. If this is the case, this is what conservation of mechanical energy tells us here. So conservation of mechanical energy shows that if the external force is zero, that means any forces other than the force of gravity and the spring force. Any other force. So if there's no force that's not the force of gravity or the spring force, then the energy before the interaction and the energy afterwards are exactly the same. So then this tells us here that the kinetic energy of one, the gravitational one, the spring one is going to equal to the kinetic energy afterwards, and something like this. This is conservation of mechanical energy right here. And this is probably the first commandment of physics. It is a big, big deal. But it's the same as the work energy theorem, but just in a different language. So let's just make a couple of remarks before we launch into examples. So let's make some interpretations of this here. So the first thing that I would say here is that how is conservation of mechanical energy used? Well, what we want to do here is that we typically are not interested in the total energy. The total mechanical energy of a system is usually useless. It's usually useless. We typically don't care about the total mechanical energy. We use it to understand how energy behaves / transforms. In other words, it's like it's an extremely useful book. Otherwise, I think bookkeeping has 2 Ks. Oops. Bookkeeping system of energy. So when we talk about how we use conservation of energy, we use it as a bookkeeping system. And then the other thing that I think is worth saying here is that why is conservation of mechanical energy so important? The thing about it is that every interaction, we only can measure two things. In every interaction, one can only measure its initial state and its final state. But nothing in between. So what I mean by that is that when I talk about if I have some interaction, just like we did with momentum, there's the before, and then there's the after. So when I look at the energy before, no, that's not what I meant to say. And then if I look at during, and then if I look at the energy after, so usually this is impossible to measure. Energy says that's fine. We don't care about that. We don't care about that. It's just going to be the same. And so what we do here is that here's where this tracking system, if we can only talk about before and then we can only talk about afterwards, what we find here is that then we use bar diagrams to track energy transformations. So for example, let's say that I have a total energy of a system. Okay, let's say that this is my total energy. All I know is that this has to remain constant, very similar to momentum. All I know is that this is the total. And this guy has to be a constant, no matter what. So now what we start to do is that we start to ask what actually happens. Well, we start to look at how the energies behave. Maybe we have a potential energy term that looks like that. Because that's a total here, that means here that the rest of this must be a larger kinetic energy. Or if this thing suddenly shifts to here, then I see that the potential gets large. As a consequence, the kinetic energy must get small. In other words, kinetic and potential energy are inversely proportional to each other. So if I'm looking at these energies, you can see this inversely proportionality because it says this. I know that this mechanical energy is always a constant, and it's going to be K plus U. So now if something changes in the system that makes K larger, we have no choice but to make the potential energy smaller. On the other hand, if suddenly the kinetic energy gets small, then the potential energy must be large. And so when we're looking at these situations here, what are we actually looking at? Well, what we mean by this is that we mean something like this, is that if we have a small kinetic energy, that typically implies a slow speed. But if we have a large kinetic energy, then this tells us that this is a fast speed. But this is also true for potential energy. So if I have a tiny gravitational potential like this, that tells me that this is a low height. But if I have a large potential energy like this, that's going to tell us that this is a high height. So the pictures now are giving us a physical situation of what is going on here. So again, and I could say the same thing with the spring. If I look at the spring, if I have a little tiny spring like this, that tells me that it has not much stretch in the spring. But if it's large, then we're really talking about is that it has a large stretch. And because it has a large, we've stored a lot of work into that. So these are sort of like these physical pictures that we want to really think about. So now we're sort of like, exactly what we want to do in order to go get some practice on some examples. So let's look at this. So what I have here is I have some problem-solving strategies. Okay, and then let's look at some examples of just setting some things up here. So it says here, step 1, identify 2 states to the system, where one state is known and the other is an unknown state. That is, one state you know everything about. That means you know its speed, you know its height, you know its spring compression. And the other state, you only are missing a little bit of the information. Maybe you don't know the speed, maybe you don't know the height, maybe you don't know the compression. But the goal is always to determine some type of position or some type of speed. Then for each state, identify the associated kinetic and potential energies of those points, and then apply conservation of mechanical energy and solve for the appropriate problem. So let's go look at some simple examples and apply this. So here we go. So as examples, let's talk about the first one here. Let's say that we drop a perfect ball onto the floor. Maybe I don't have to say perfect, but let's do this 2 ways. So now what we're going to do here is that I imagine that I have a table right here. And then I'm going to drop a ball right here. I'm going to drop my ball. And all I know is that what we're going to do is that when we drop it, eventually it's got to do what? It's got to come all the way down to here. So what actually happens here? So here's what I see here. I'm going to isolate the system. Okay, I'm going to come in here and I'm going to isolate the system. Now that I isolate the system, I says, what are the forces acting on this ball? Are there any external forces or are there any forces? And one of them, there is the force of gravity. Now, if I drop this ball onto the floor, we typically assume no air drag. And so are there any other forces? And so that means here in my system, it's really the ball plus Earth, because I have to include the force of gravity. Is there a spring force? No. Is there any other force? The answer is no. So because work external is 0, that means it's a force. It's the only forces I can consider are the spring force and the force of gravity. Then that means that the total mechanical energy is now the same, which then tells me that the energy before must be the same as the energy afterwards. So I know mechanical energy is conserved. So then I start to look at the details. What do I know? Let's say that when I look at state 1, I'm going to call this state 1, and I'm going to call this state 2. So what is known about state 1? Well, even though I didn't mention it, let's say that we do know what the height of 1 is. And we're going to say that this height, y2, will set it equal to 0. So what we can say here is that, let's say that the ball starts at rest from height y1. So when I look at the total energy of the system, I could then say that the total energy of the system is then going to be K1 plus UG1. But if it's starting from rest, we immediately know that that guy is 0 because it's starting from rest. So when I look at my bar system, it's telling me that I have this amount of potential energy. My energy 1 is completely gravitational potential energy. And since I can't create or destroy energy, this energy is a fixed quantity. It is a constant no matter what. So then I want to know what's happening at state 2. So at state 2, I could then come over here. Let me move this over here. So then I could ask the question, what do we know about state 2? Well, its height is 0, which then tells me that its gravitational potential there is 0, but we do not know its speed. So then what we're seeing here is that at this state, state 1 is a known energy. State 2 is an unknown energy. In other words, conservation of mechanical energy says that I know everything about energy 1, but I don't know everything about energy to? It's an unknown. So when I look at this thing, I could then come over here and just say, when I get to the bottom here, I see that the gravitational potential energy is 0. Here, we see that the kinetic energy at 1 is 0. So then we are forced to conclude that all of the potential energy has transformed into kinetic energy. So then, this is my bar diagram. My bar diagram then says, if I look at these energies, it says that I have K1 plus UG1. That's going to equal K2 plus UG2. From the bar diagram, we can clearly show that that is 0 because it starts at rest. This is 0 because it's at the ground. So now I can rewrite this as mgy1 equals 1/2 mv2 squared. So right away, this now gives me an equation that this allows me to solve for V2. So conservation of energy is setting this stuff up here. Let's look at a different situation. Let's look at one more example, and it goes something like this. And this will, what we're going to have here is that we're going to have a cart bouncing. I guess I should say bouncing off a spring. Okay. So we want to set this up so that we don't add friction to the situation, because I'm not going to give you a friction problem on the exam. So my picture then looks something like this. So I'm going to imagine that I have a frictionless surface with a cart colliding with a spring. How much compression occurs? So picture-wise, I imagine that we have a frictionless surface, and at this end, I have a spring. And the only thing that I know here is that I'm going to have a cart coming in. So it's essentially a sliding block. We can't talk about rolling. So this cart is coming in. And what I'm going to say here is that we expect that if I know the initial speed, let's say that this guy comes in with some speed 1. Okay, so this is a known quantity here. So now I ask about my system here. So when I look at my system right here, note that, are there any forces acting on this thing? And the answer is, yeah, there is a force of gravity, but there's also a normal force. So that tells me that when I look at the net force acting on the system, that net force is going to be 0. Because I have equal and opposite forces. So I'm going to get, let's say, normal minus mg. That's going to be 0. So those forces, they do not change the energy. The only time we care about this is when I have this situation. We don't care about out there. We care about what happens when there's a collision. We only care just before and after the collision. So then if I redraw this thing here, here's my system here. What I really need here is that I need this block to be right here. That's what we care about. So when I look at this, this is the before. And then afterwards, what happens? The spring has now compressed. And so I can see that during this process, a compression has occurred. So now if I look at my system here, what is my system? So my system here, I'm seeing that I do have a force, and this is the force of the spring. Gravity and the normal are not going to contribute to this. So now we know that the spring force will take all its work and convert it into spring potential energy. So now this is what I have afterwards. And so afterwards, if we want maximum compression, that means that its final speed should be 0. So then I start drawing my picture. So what does my picture says here? It says that I have a total energy. And this total energy, because the only force is friction here, this total energy has to be a constant. And so when I look at this thing, right before it collides, there's no spring interaction. So right before, all of this energy has to be in the form of kinetic energy, where the spring potential energy at 1 is 0. So if this is the case, then I don't have to worry about what happens afterwards. I don't care how this thing is compressing. All I know is that in the end, if I look at just the endpoint, I know that at K2, it stops it. It gets maximum compression. So then this tells me that the rest of this is only spring potential energy at 2 here. That's my equation right there. That is completely my equation. So when I look at this thing, note that I didn't include gravity, so I don't have to worry about gravity. But then I start to look at this thing and it says, what is the energy before? What is the energy afterwards? And then we start to go, okay, I have this amount of kinetic energy. I have this amount of spring potential energy. And then afterwards, I have that amount of kinetic and I have that amount of spring. So when I start to look at these guys have to be identical, but there was really no contact with the spring. And here, this we brought to a rest. So then conservation of energy tells me that it has to be like this. So then I could then come in here and write that this is 1/2 mv1 squared plus 0. That's going to equal to 0 plus 1/2 k x2 squared. So again, what you're seeing here is that we have now set up an equation. So we set up an equation to solve for x2. So conservation of energy is giving me that ability to do that here. So here's what I'm going to propose. There's one example that I think is worth going through, and that's example 7.3. And I'm going to suggest that on Wednesday I come back and I do example 10.3. And I want to give you 2 days to do the exam so that you have Wednesday and Thursday to actually complete the exam, to try to extend the period of you taking that exam. So if I come back on Wednesday, I'm still going to record it, but I won't be uploading it till later on, sometime after 2 o'clock. So my question to you, does that seem reasonable to you? And I'm assuming that more than likely that you are happy to see me do that. So I think I just want to make sure that we're clear on what I'm trying to do here. I don't think the exam is going to be any tougher than some of the examples we've already done. And I think the reason why is that me having to teach from home, I know that I have put you at a huge disadvantage. And so because, that situation, I'm not going to test you the way I would normally test you. There's no way. I don't think that would be fair. So the idea here is that you have to be able to understand the image of what's your system. Do you have external forces? Are the forces changing the momentum? Are the forces changing the energy? If they're changing them, you then have to apply the impulse momentum theorem or the work energy theorem. If they're not changing them, then that means that the impulse is zero, and therefore I can use conservation of momentum. With energy, if there's no external work, that means you can include the spring force and the force of gravity into your system, but if I have any other force, then I can't use conservation of energy. But if the only two forces in my system are spring force and gravity, then conservation of energy could be used. So then you could compare the energy before and the energy afterwards. So I know that I'm a little bit earlier. There's 10 minutes, but I'm going to be smack in the middle of this example, and then I won't be able to really complete it. And I'd rather complete it from start to finish. Now, the reason why I think it's important to do this example correctly, because it actually talks about choosing different references. That's really what's at issue here. Because there's a hard way and there's an easier way to pick good references. And so if I, for example, share my screen really quickly, I'm talking about this example right here. And what you're seeing on this example, there are various heights. And really what I would like to do here is start right here. Should I choose my y equal to 0 here, or should I choose my y equal to 0 here? That becomes a really important, conceptual thing to actually look at. And I think that this is a really good example to actually do. And that's why on Wednesday, I want to come do it. But again, I want to give you those days to do that. So I'm going to stop here. I'll record this. I mean, it's already recorded, but I'm going to stop it here and I'll edit this and upload it as quickly as I can. And then I'll see you on Wednesday and I'll see you in lab tomorrow. Okay. I'll talk to you soon. Bye.